Good evening. Thank you all for being here tonight. I wanted to welcome everyone. This is our third Sea Secrets lecture of 2020. At this time, I wanted to ask everyone to turn off your phones, your watch, your tablet, whatever you have that might go off in the midst of all of this. My name is Jennifer Dillon. I am the Executive Director of Development here at the Rosenstiel School. And tonight we're going to be hearing from Dr. Everette Joseph from the National Center for Atmospheric Research. Thank you for being with us, Dr. Joseph. Appreciate it. Before I move on, I'd also like to thank you for joining us tonight and to recognize all of our Sea Secret sponsors and the many other friends and family who contribute to the Rosenstiel School. Thank you to Bank of America, the Shepard Broad Foundation, Meredith Ann Dasberg Foundation, William J. Galway III, Cheryl Gold, Key Biscayne Community Foundation, Elizabeth C. Lambertson Foundation, Joan McCann Family Foundation, Taylor and Melissa White Fund, Myron and Nicole Wang, the Welch Family Foundation, and Southern Glazers Wine and Spirits. Thank you very much. If anyone here is not already a sponsor, if you'd like to become a sponsor or support the Rosenstiel School, you can see me after the lecture. You can see me during the receptions, usually before they happen. I'd be happy to share any way that you can help us if you'd like to do that. Now's the time. It's my pleasure to introduce to you Professor Amy Clement. She's going to present our student spotlight this evening. Dr. Clement is a professor in the Department of Atmospheric Sciences at the Rosenstiel School. She is an expert in climate modeling, and in her research, she strives to understand the mechanisms of past, present, and future climate change. She earned her bachelor's degree in physics from Columbia College and Ph.D. from the Department of Earth and Environmental Science, both at Columbia University in New York. She did a postdoctoral fellowship at the University of Pierre and Marie Curie in Paris, France, and has been a faculty member here since 2001. Amy has made a mark in her field by motivating scientists to think more about the role of the tropics in the paleoclimate and encouraging them to simplify the climate system in order to better understand its fundamental processes. She teaches courses on atmospheric science, physics of climate science policy, and climate and society. She mentors graduate students and our postdoctoral students in the atmospheric and ocean sciences. And she prepares her students to go on to successful careers where they can make an impact in their fields. In 2015, she was awarded the Rosenstiel School Outstanding Faculty Mentor Award, and it's a student-nominated award that recognizes mentors who go above and beyond to ensure the success of their students. Thank you, Amy. Welcome.
Thanks, Jennifer. Thanks, everyone, for coming. It's so great to see so many people out here tonight. We're going to be hearing from Everette Joseph in a little bit, but before we do, our tradition is here at Sea Secrets is to have our wonderful graduate students give you a little brief overview of the kind of work that they're doing. And I have the great pleasure today to introduce my own graduate student, Jeremy Clavins, who's here in his 5th year of his Ph.D. at the work at the Rosenstiel School. He got his undergrad here at the University of Miami in ecosystem science and policy, went away to Chicago, where he got his master's in environmental science and policy at the University of Chicago. And then it wasn't that hard to lure him back when he came on a recruiting trip in February to Miami from Chicago. And he came back to work with us, to work with me on the topic of climate variability in the North Atlantic, looking at ocean temperatures in the North Atlantic and how they fluctuate from decade to decade. As the waters warm and cool, our expectations of change for regional weather, such as hurricanes and rainfall over Florida. And if we want to predict these changes in advance, we ought to know why the warming and cooling happens in the first place. And Jeremy and his collaborators are going to explain to us a little bit about the work that we do in the lab and the work that is earning him a PhD here at the Rosenstiel School. So, Jeremy.
Good evening, everyone, and thank you for that kind introduction, Amy. Today I'm going to be talking about my work towards my Ph.D. and my group's work as a whole, focusing on climate variability in the North Atlantic. None of this would have been possible without the hard work of my collaborators and, of course, the generous guidance from my advisor, Amy Clement. So why should we care about climate variability in the North Atlantic? Well, first, we live right next to it. It's right there. One of the most important reasons, a big example that we can think of, is that even though it's March, we still care about the hurricanes that form over the Atlantic. And if we look at the recent history of hurricanes in the Atlantic, we see something interesting. And that is there seems to be periods of high hurricane activity and low hurricane activity. This plot from NOAA shows a measure of hurricane activity in the Atlantic. The taller the bar, the more activity there was that year. These periods of high and low activity can last for decades. In the 50s to late 60s, over on the left there was a period of high activity. In the 70s through mid-90s, it was a little quieter. And of course, now we're living in a fairly active period. So why is hurricane activity changing over these long periods? Well, this pattern of hurricane activity seems to go pretty well with the history of sea surface temperature in the Atlantic Ocean. You can see that our periods of high hurricane activity in the 50s and 60s go with above average temperatures. That's the kind of red bars there in the red shaded area. And the periods of low hurricane activity is happening around the same time as cooler temperatures in the 70s and 80s in the blue there. And if we put these two metrics together, we see that they match up really well. In the gray, we have hurricane activity, and the pink dashed line there, looks a little bit purple here, we have the Atlantic sea surface temperature again. So warmer Atlantic temperatures are associated with more hurricane activity, and cold Atlantic temperatures are associated with less hurricane activity. And so these Atlantic Ocean temperatures seem pretty important. And one of the central questions of my thesis is, why do Atlantic Ocean temperatures change over many decades? What's the cause of these long swings in ocean temperature? And one of the best tools that we have to answer these questions are climate models. And in particular, we're going to use the Community Earth System model, or CESM. This model is developed at NCAR and analyzed by people all over the world. This model puts together all the best science about each of the individual components of the Earth system, the atmosphere, the ocean, the land, sea ice, all into one big computer program. And we can use this program to learn a little bit more about the Earth. And one of the things that's really cool about CESM in particular is that it lets us learn about the Earth by doing experiments on a really simplified version of the Earth. And if we want to figure out why the Atlantic gets warm and cold over long periods of time, we can think of some of the potential causes. For example, changes in the atmosphere or changes in the ocean. And we can do an experiment. And just like you did in your high school or your college science classes, we start with a control case. That's going to be our best model of the Earth. And that best model, we're going to include the most realistic ocean model that we have. And then we're going to take that model and we're going to break it. We're going to make an experimental case. And we're going to replace our big fancy ocean model, this is a very technical graphic here, with a little simple ocean model. And now this simplified ocean doesn't have any ocean currents or any real changes in time. It just kind of sits there. And we can compare these two models, our control case and our experimental case. And we can see how the Atlantic Ocean temperatures compare. If they're different, it's because we know we got rid of the ocean currents. And if they're the same, well, then the ocean currents weren't super important for this particular problem. So here's the result from our full model run at NCAR. Observed Atlantic temperatures are in the black line there, and each of the thin red lines are the 41 runs of this full ocean model with the big fancy ocean involved. And it does a pretty good job of getting observations. The model does a pretty good job of getting observations. It's not perfect, but it's pretty good. And we can compare that to our experimental case. Those are the thin blue lines on the plot on the right. And we see that it also does a pretty good job. Actually, it might do a better job. So these swings in Atlantic Ocean temperature don't seem to be related to the ocean currents. Well then, what is it? Well, believe it or not, these plots actually show us the answer. Atlantic Ocean temperatures contain both signal and noise. It's just like seasonal temperature. So we expect that, on average, summer in Miami is going to be hot. But there are some days where we get kind of lucky and it's a little bit cooler. We get a break from the heat. And there are some days we get unlucky and it's much hotter. But on average, if you average across all of those lucky and unlucky days, you find out that summer was hotter than the rest of the year, just like you expected. And the same thing's happening on these really long timescales. There are years that are lucky and there are years that are unlucky. That's why the thin red lines and the thin blue lines spread out so much in each of the individual runs of our model. And when we take the average, that's going to be the thick red line going along the middle there and the thick blue line going along the middle. That's going to be our signal. And we see that that signal, the thick line, goes along pretty well with observations, the black line. And so we think it's the signal that's causing changes in the observed Atlantic temperatures. What is this signal? Well, that's the information that we give to the models. Things like the concentration of greenhouse gases, the amount of aerosols from industry, or the amount of aerosols from volcanoes. And we think that it's those changes in what's in the atmosphere that's changing Atlantic Ocean temperatures on these really long timescales. Thank you. Sure. Happy to take a couple questions if they're all right.
Okay.
Or you can find me afterwards.
Yeah. I'll be around after. Thank you so much, Jeremy. I really enjoyed that. Very proud. So next, it is my pleasure to introduce Dr. Everette Joseph, who is visiting us from NCAR, where all these experiments were done. Actually, they weren't done at NCAR. They were done at a supercomputing center in Wyoming that NCAR runs. Everette is the director of NCAR. It's the National Center for Atmospheric Research. It's an NSF federally funded research laboratory. It is, I will describe it as the mecca of atmospheric science in our field. It is in an amazing building right at the base of the Flatirons in Boulder, designed by I.M. Pei in the 60s? 60s? If anybody's seen the movie Sleeper, was it in that? Okay, War Games. It's been in movies. It's an outstanding building. And what's even more impressive is the research that's done inside. And you'll hear more about that from Everette. He's the director of it now since 2019. But let me tell you a little bit more about his prior life before he became the director there. He was originally came from the Caribbean, grew up in the U.S. Virgin Islands, moved to New York City, and went to high school in New York City, and then colleges at SUNY colleges, and did his Ph.D. in atmospheric science, in physics at SUNY Albany. He took a little break from studying physics and high energy physics to work for New York State. And while he was doing that, he was starting to learn about climate. It was actually a time when many of us were getting interested in climate change in the late 80s and early 90s, learning about how we're impacting the climate system that was already understood by many scientists at the time. And he got interested in it and decided to go back and get a PhD in physics, but working on atmospheric radiation and looking at how radiation from the sun and from the earth moves through the atmosphere. That was the beginning of what is, I would say, a really outstanding career. I'll give you a few highlights that I'm going to read from here, which is that he went first to Howard University, where he was a professor, and at Howard University, he was working in the university's program on atmospheric science, dedicating himself to teaching and mentoring and inspiring the next generation. He served as the director of Beltsville Center for Climate System Observation and NASA University Research Center. He also brought together colleagues from Howard, NASA, NOAA, Penn State University, of Maryland and Baltimore and other institutions to develop an interdisciplinary, multi-institutional, multi-agency center studying key atmospheric processes with relevance to predicting weather, climate, and air quality. After that, he moved back to New York State and went to SUNY Albany, where he was co-led a $30 million New York State Mesonet network for advanced weather detection in New York State. He also served as principal or co-principal investigator on over $90 million in research grants from NSF, NOAA, NASA, and the Army. He joined the UCAR Board of Trustees. So UCAR is a university center on atmospheric research that manages NCAR in 2011. I actually had the pleasure of serving on that Board of Trustees with Everette for 3 years. We got to go to Boulder a lot, which was really fun, and Washington, D.C. to lobby on behalf of the atmospheric sciences to policymakers and members of Congress. I want to just talk a little bit about Everette. He has an enormous list of ways that he's served the atmospheric science and climate community through serving on National Academy of Science boards and American Meteorological Society's commissions. But he is one of those unique and rare people that can be both a stellar scientist working on really important research questions, and also leading research in labs, in the lab, in the field, and leading these giant institutions which are so important to our field. And I'll just mention a few things about his research and field work. He spent many years traversing the Atlantic right out here, well, a little bit further east of here, 10 times going north and south in the Atlantic across the equator, measuring smoke, dust aerosols, atmospheric radiation, and ozone, and learning about the exact things we didn't plan this necessarily, that Jeremy was talking about, these changes in atmospheric composition that drive long-term changes in climate that lead to impacts for us here in terms of hurricanes and rainfall. So it's really exciting to have him back here. The work that work in the Atlantic was in partnership with the people across the street here at the NOAA Atlantic Oceanographic and Meteorological Lab. And it's really exciting to have Everette back here to talk about the work that he's been doing at NCAR, and we'll hear a little bit about his career and what led him there. So thank you for joining us, Everette, and Dr. Everette Joseph.
Says Everette Joseph. Yeah, perfect.
You want to try? Click cancel.
Yeah. Hold on,
So as a professor at heart, I hate being changed behind the podium, so I'm going to walk around. Thank you so much, Amy, for that very generous introduction. That was very gracious of you. And excellent job, Jamie. You're going to be a tough act to follow. I'm very honored to be here and today to share some thoughts with you about what we're thinking about at NCAR and the broader scientific community. Not the least because of the weather. I left Boulder and it was like 20 degrees and snowing. It's been a terrible winter in Boulder. When I interviewed for the job, they promised me something like 100 days of sunshine, and it's just not been that. So given my Caribbean roots, it's a real pleasure to be here in warm, humid Miami. So thank you very much. I'm in my element here. So today I'm going to talk to you about, again, some things we're thinking about at NCAR and I think in the broader scientific community about actionable Earth system sciences. And so the science is really thinking carefully about how we do science in a way that's really important and impactful for society, and that's really responsive to the grand challenges that we're facing here today. Okay, I'm going to try to forward this thing, and I bet you it's going to go backwards. There you go. So as you know from the media today, in society, we're facing some serious global threats that are, in a sense, unprecedented in modern history and in a sense, existential to our society. And atmospherics, as Jeremy, in his presentation, as Amy talked about, atmospheric scientists have been working really hard, and we continue to work really hard to try to understand the atmosphere and to try to understand the Earth system with the ultimate goal of really helping society to mitigate some of these challenges and to really build a more resilient society against these threats. And so I'm going to briefly touch on some of the successes that's resulted. That's really obvious to you, but I'll point them out, of this sort of work that we've been doing in the atmospheric sciences community, and how we're thinking about evolving that research so that we can be more directly beneficial to society. So air quality, for example, air quality is one of the greatest environmental threat to human health. And that results from emissions from automobiles and from industry and from other activity. And the impact is significant. So if you look, pretty much most of the planet, 6.7 billion people live in conditions of excessive pollution. That's from a UN study. And on the order of 4 million, there are 4 million worldwide fatalities as a result of poor air quality. Now put that into context. As we know, there's a great concern today about the coronavirus that's spreading. That's very serious. In that context, there's discussion about fatalities with respect to the flu. And I think I looked it up. Don't quote me on this, but I think fatalities associated with the flu is on something of 500,000 or so worldwide. Fatalities associated with road accidents are about 1 million or so. So while those things, any fatality is horrible, right? But putting this into the context, and this is something that we live with daily, fatalities is on the order of 4 million fatalities a year globally that's a result from poor air quality. So that's, I think, an important context to have. This is a mudslide that occurred in Washington State in 2014 that was devastating and resulted in fatalities. And it's an example of increasing extremes that we continue to experience here globally, and I think that's widely reported in the media. And so here we see that in 2019, 14 weather events were on the order, in terms of economic impact, were on the order of $1 billion. And it was the 5th consecutive year of events that were 10 or more events that were on the scale of $1 billion. So we're experiencing these increasing trends of extremes. Another topic that's popular in the media are wildfires. Wildfires not only impact infrastructure, obviously impact health, life, and property, but also impact air quality. It has a tremendous impact on local air quality, regional air quality, and air quality across on a continental scale. In New York, some of the research that we were doing in New York was really looking at the impact of Western fires on the air quality in New York State, and we saw significant impacts. So wildfires are increasing because of climate change, forest management in the wake of development, and other issues like that. And so in the United States alone, the economic impact is on the order of over $100 billion a year. And just this event in California in 2018 resulted in about $11 billion in fire insurance claims. And obviously what's been in the media has been the wildfires in Australia, and God knows what the economic impact of those are. This is a life cycle of a solar flare from build up to this explosive release. And it's the first time that this has been simulated in a single model. Scientists at NCAR essentially embedded this process into a model and able to provide this simulation. This work was published in Nature Astronomy recently and has been widely reported. So it's a great accomplishment by scientists at NCAR. But what it's enabling is, in this simulation, it's enabling simulation of solar activity. For example, sunspots that are associated with flares and coronal mass injection. And coronal mass injection can be very impactful, and so we call this, in a sense, space weather. And that can be very impactful on our infrastructure, on our communication satellites, and on our electrical grid. To the extent that something like 4 to 5% of global GDP is at risk for a solar storm, similar to large ones that have occurred in the past. And we're becoming, as we become a more connected society, right? It becomes we're more at risk. I was talking to someone about a Tesla, and we had test drove one. And this was a solar scientist, and they said to me, well, you know, if we have a big solar cycle like this, and you're out in your Tesla, this is no bad advertisement for Tesla. But this is the scale of this impactful. So I didn't intend to be doom and gloom here and sort of depress you from all the hazardous weather and the threatening weather and threatening conditions. And so I think what this figure is really designed, this image is designed to really show that scientific advances, and you're well aware from where you live here in Miami, has really greatly benefited society, and we're enjoying tremendous benefits today from scientific advancements that has made our society more resilient. And so again, I don't want this message to be all gloom and doom, and I think this is an example of that. Satellites that are our system of satellites. Observation satellites for weather, but for air quality and for other phenomena, as well as aircraft surveillance and other observations, combined with numerical models, numerical weather prediction, produce forecasts that's very valuable to us, that when combined with decision making, really allows the public to react more swiftly to these events, and has resulted over the years, if you think about over the last 80 years or so or more, has really resulted in a significant reduction in the loss of life. Think back to the Great Storm of Galveston. The fatalities associated with that were in the order of 8,000. Think about that. Think about the loss of life from one storm on the order of 8,000. That doesn't happen today. And so I think it's important for us to celebrate, again, not being all gloom and doom, but there are real advances that we enjoy from scientific advances that has occurred over the many years. However, the message is really we're still at risk. And the question is, from within the scientific community, how can we be more deliberate to reduce that risk? And this is an example of that. This is Matthew, roughly 3 days out, and so this is the probability cone. As you can see, there's probability of landfall, all along here, and that's a great area, 3 days in advance of landfall. That's a great uncertainty. The kind of uncertainty not to be able to make any kind of precise decision making, and can be expensive, and also can be dangerous. And so as a scientific community, we need to be able to do better than that. And that's kind of where I want to focus. This is an example of severe flooding that occurred in Texas in 2018. Climate models that sort of forecast the future change of these kinds of events disagree on the order of 50%. This is sort of flooding due to runoff in the southwest US. And if you look at these models, and NCAR scientists have in some of the runs that Jeremy talked about, the long-term runs, the climate models agree widely. And that's problematic if you're a water resource manager. If you're a water resource manager and you're thinking about water resource planning, say 10, 15, 20 years ahead, this kind of uncertainty is unacceptable because there's no real actionable information for you to plan. So what we need to do is we really need to reduce uncertainty in prediction that provide actionable information for decision makers, for communities, for governments. And so from how we do our science, and so I'm going to get a little bit inside baseball here, maybe, in how we do our science. It's sort of, how do we really create, from the organizations like NCAR and these big organizations that are really managing and advancing science, is really thinking hard about how we do that. How do we produce science with and for society? And traditionally, we talk about curiosity-driven research. At the NSF, if you write a proposal, what they're really big on is really funding curiosity-driven research, where you're a scientist and you have an idea, and it's a neat idea, and you go out and you get funding and you pursue that neat idea. And it's just curiosity. And as a result of that, there might be serendipity, for example. And really what you're pursuing, what's fundamental to the work that we do, is that you're pursuing understanding. You're pursuing understanding of the atmosphere. You're pursuing understanding of the Earth system. And so I think that, and this is to some extent controversial, I think that that there are questions to purely to the effectiveness and relevance of purely pursuing curiosity-driven research in the context of grand societal challenges that are existential. And so this understanding approach, so that example I talked about earlier about the uncertainty in models, and actually Amy is more of a climate expert than I am, but I would argue that that uncertainty is sort of assumptions that are made by a really small handful of people in the development of these models of things that we don't understand, but that's kind of curiosity-driven and not solution-driven. And so they're making assumptions about these things that are really sort of not solution-driven. And one may argue that engineers are kind of more solution-driven. And so we have these uncertainties in the system. So what I argue for and what we argue for is sort of a blending of curiosity-driven research and what we call use-inspired research. Research that's really focused on and motivated by a challenge and sort of really pursuing a solution to that challenge, not just pure curiosity. Hopefully you're following me. I told you I get a little bit inside baseball here. I look forward to questions about all that. And so sort of moving towards this blend of more deliberate use-inspired research, there are methods to that. We call convergence research, co-design, transdisciplinarity. These are all methods in a way of use-inspired research. At NSF, convergence research, and I'll talk about convergence in a minute. The NSF, back in 2016, as part of what it calls its 10 great ideas to guide its funding, one of the 10 big ideas is called convergence research. And what is convergence research? The characteristics of a convergence research is, one, it's really driven by a serious problem, trying to find a solution to a serious problem that's impactful to the society. The other piece of it is integration across disciplines. Not isolating disciplines, but integration across disciplines where you have many disciplines coming together to work on a solution. And what's really interesting about that is that as disciplines come together, they bring their different way of speaking, they bring their different methodologies, they bring their different cultures. And in that way, what happens is that really new frameworks and new ideas grow out of that, rather than being isolated with respect to disciplines. So that's kind of the concept that we're thinking about with respect to convergence research. We also use the term co-development. So at NCAR, we're pursuing this. We call it actionable Earth system science. And so we're doing this. And what we've done is, and we worked hard. When I got to NCAR, they said, your first job is to write a new strategic plan, like a true bureaucracy. So I spent the whole year writing a new strategic plan and embedded this whole notion, this whole idea of convergence research into that strategic plan. And what we did was we essentially talked about organizing, in the strategic plan, talk about organizing and set goals for organizing our research into 4 grand societal challenges. 1, public health. 2, infrastructure. 3, increasing extremes. And 4, scientifically sound responses to climate change. So again, organizing our research into problems that are challenging for society. And so that's the first aspect of this actionable Earth system science and convergence. And we commit ourselves to being more deliberate to this actionable science approach or convergence approach. Every strategic plan needs a lot of diagrams, and so here we have the challenging scientific problems of climate, vulnerable infrastructure, health, and extremes. And the paradigm that we talk about is continuing to do, we got a lot of debate, we got a lot of argument about this because people said, oh, you're going to change NCAR into being, more applied, more engineering. You're going to abandon this basic research. And we're saying, no, we're not doing that. We're going to continue to do our basic research. But we want to do our basic research in a way that's more informed. And so this diagram really illustrates that we co-design, or we're convergent in the basic research that we do, where we bring stakeholders, key stakeholders, other disciplines, into setting requirements, into the discussion as we pursue our basic research. And the thing that we do, and so at NCAR, we're really focused on enabling research in the university community, like here, like Jeremy's work. And so the university community are important partners for us, as well as other partners. But we bring them in other disciplines outside of atmospheric sciences, but not wildly outside of atmospheric sciences. We're talking about engineering, for example, or physics, but also social human dimension as well. To co-design the basic research, to set requirements in the basic research that we do, so we can have more actionable outcomes of that work with a societal impact. And we form partnerships to ensure that those outcomes are actionable towards decision-making, towards producing, for example, numerical models that can then provide a forecast with a much narrower cone of landfall. So I'll give you a few examples. I have too many, so maybe I'll cut some of them off and allow time for questions. But I'll give you a few examples of work that we're doing that exemplifies this approach. This is the National Water Model, and run by NOAA. And it's really built on a model at NCAR that was developed at NCAR that we call WRF Hydro. So what you see is that these pulses that you're seeing is really stream flow over the month of May and June, I think. of stream flow, these pulses of stream flow that's response to weather systems that are propagating the continental U.S. And this model is a significant improvement of what existed before. Stream flow models, for example, they provided forecasts on, say, thousands of points. In the case, this model is across the continental U.S., and it produces forecasts continuously at millions of points. So a lot more information for decision makers and for forecasters to use in warning the public. Work continues to validate the model. But I think this is a good example. And to develop a model like this, it's not just about the precipitation that comes out. At atmospheric scientists, we worry about the stuff that comes out of the atmosphere. Hydrologists calls it the 2D, the 1D problem, just the rain. We just care about the rain. We want to make sure we get the rain right. But that's not what you care about. I mean, you sort of do, right? You know, if you're having a party or something like that. But the real risk is the flooding. And at atmospheric scientists, we don't worry about the flooding. We want to make sure we get the rain right. And so again, this is an example, what am I talking about convergence research. If the problem is the flooding that's going to kill you, then we should work with hydrologists, land people, and a whole bunch of other people to ensure that we get the flooding right, not just the rain. And that's what this model does. And the development of this model required a really multidisciplinary expertise. Hydrologists, atmospheric scientists, engineers, and others to get this right. This is an example. This is the Colorado Fire Prediction System. And at NCAR, there's research to develop fire models. I talked about fires earlier. And this is an example of a system, again, that's co-developed and is producing predictions in a way that's useful. This is an example of what they call the Cold Springs Fire in Colorado. And the neat sort of basic research issue with respect to this model is that it's one of the first models. So fires produce their own meteorology unto themselves. And so in this model, what the scientists of NCAR have been able to do, plus the scientists of the university community, is couple the weather that's produced from the fire with the background meteorology. So you get a system that's better able to predict the evolution of the fire, because that interaction is really important to how the fire evolves. And what they're doing is they're working with emergency managers and others to better develop that system, again, so that it can produce better prediction. I'm sure I'm running long on time, so I won't go through this one, but basically they're working with emergency managers, so not only to on the coupling aspect of it, but looking at how to represent more dynamically, for example, the fuel source that feeds the fire. How am I doing on time? How many more minutes? Okay, yeah, I'm almost there. So this is an example of, this is called a large Eddy simulation model. And as you can see, what it's doing is, this is a simulation over Oklahoma City. And these are the building structure over Oklahoma City. And if you look carefully, what you can see is the impact of the buildings producing wake. So the impact of the buildings on flow. Normally, given the complexity of that process, this is a very computationally intensive simulation, and one that's really not practical for what we call operational application. So it's really not useful for us to use to do forecasting, for example. But the scientists at NCAR and other scientists have developed this model called Eddy on GPU, graphical processing technology, GPU technology. And that development in GPU has made this model way more efficient than on regular CPU. So as a result, because of that development on GPU, graphical processors, this model can now become operational. And an operation like this have really important implications for wind energy, and also for drones. We're doing research with drones in two ways. One, we're using the drones because drones are taking weather observations. There's a lot of research that's going on that are using drones for weather observations, and they get these fine information about fine-scale processes in the atmosphere, and so we can use the data from drones to verify this model. But to realize, there's a lot of stuff in the media about Google and Amazon delivering packages on your doorstep. And they're doing a lot of research. I was involved in some of that research at Albany. But to really realize that, they're going to have to know the weather, because drones don't do well in weather. And if you want to do that kind of operation in a city, in an urban canyon, you're going to have to know that stuff. And so that's some of the work that we're really excited about in order to maybe enable delivery of your Amazon order to your doorstep. I'm going to skip this one, but this is just an example of air quality. Obviously what's near and dear to the hearts here of people in Miami is hurricane intensity and track prediction, and we're doing work on that as well. In this particular case, we're using what we call deep learning to looking at patterns of intensification in our hurricane model, and essentially using those patterns to help with the forecast. And that's proving to be quite successful in that area where we're outperforming just from the deep learning, we're outperforming the regular hurricane models in terms of predicting intensification. Rapid intensification is an important characteristics of being able to forecast the storm, and we're doing much better with this kind of technology. Okay, so it's not just about, and these are my final two slides, it's not just about the technology and the research. It's also how we do our business. It's about, at NCAR, what we're thinking about is the next generation. And it's sort of producing the next generation workforce with this sort of bilingual nature, if you will, of thinking about curiosity-driven research and use-inspired research, and approaching it from that perspective. And as a university, and I'm sure the university professors here would agree, the next generation is really hungry for that. A lot of students I meet and talk to, they want to know, they're really excited about doing atmospheric science research. We call them weather weenies. But at the same time, they're also socially aware, and they're socially interested. So they just don't want to do just the atmospheric research in of itself. They want to know how to collaborate and how to interact with social scientists so that their work can be more impactful. So we're thinking about that at NCAR, how we do that. Also, we think it's important to really build a diverse scientific workforce. Because we're a country that's diverse and becoming more and more diverse, and so we think that that's important. We're thinking carefully how, again, as I talked about earlier, how we interact with our partners, not just interacting with ourselves or our university colleagues, but going beyond that and working with other partners in this sort of convergent environment. I just threw this in at the last minute, but we're thinking of convergence not only in the research what we're doing, but in the various methodologies we have. So in computing is something I think about a lot because it's a very dynamic environment. AI, data science, cloud. Right now, we're buying the next, Amy talked about the supercomputing center that we operate in Wyoming. It's a very expensive center. And we're about to buy the next supercomputer, literally, in about a couple of months, I have to sign a $30 million check. But as you know, it's a dynamic environment. And so I'm thinking, okay, is this, like you buying your laptop, is this thing going to be obsolete in 2 years? So I lose sleep at night thinking about that. I'm going to sign that $30 million check, and the next thing you know, that machine is going to be obsolete in 2 years. So I constantly ask the people who are leading this, I say, are you sure? Are you sure? Should we be going to the cloud? But we have really smart people at NCAR. But the point is here is that the point is here, it's a very dynamic environment. And so we're applying convergence here. And our goal is really to enable, it really enable discovery in Earth system sciences. And so how do we bring together all this stuff? How do we bring together AI, data science, in a way that really results in Earth system sciences discovery? And we want to move away from the traditional way of doing that. In this particular case, that's a value chain approach where the physical scientist says, oh, I have an idea, then gives it to the software engineer. And then, we want to approach that from a convergence approach where the software engineer and the physical scientists are in the room together, sort of co-designing the solution. So, So I'll stop there. And really what we're really trying to do is we're trying to really accelerate progress through. Our goal is really a thriving and sustainable 21st century society. And we're thinking in this way. We're really trying to stretch our thinking so that we conduct our research in a way that achieves that. So with that, I'll stop. And that's a view outside of the building that Amy talked about. I thought there was a picture of the building, but there's not. But that's a view outside of the IMPay building. And it's a really fantastic building. IMPay was a genius. I discover stuff every day about that building. So thank you very much for your attention.
So we have time for questions and some microphones we're going to pass around, so don't be shy.
Excuse me, I have a question, layman, very layman. It really bothers me to see cars, I wouldn't go into a garage with carbon monoxide and just sit. And it bothers me so much that, is there any studies on the effect of gas carbon monoxide pouring out of all these cars as opposed to pure electricity? Just assume we could eliminate the carbon monoxide in the atmosphere. And is that any big factor?
Yeah, well, certainly there's, and I don't have numbers ever present in my head, but on this issue of mobile source versus stationary source, electrification of vehicles will sort of transfer the emission to stationary sources, to the utility, and then you have more controls on that. So in other words, if you have an electric vehicle, it's still using energy, but that energy is coming from a power plant, and the emissions is coming from the power plant. And the chemistry, I'm not that. I know from atmospheric sciences perspective, what we're really worried about is ozone, and we're worried in terms of ambient pollution. What we really worry about is ozone, which is poisonous, and results in all kinds of respiratory issues. And we also worry about aerosols, PM, which can result from the combustion. And so that's what we really worry about from the ambient, emissions. Carbon monoxide, certainly you don't want to do that in a closed driveway, in your closed driveway. Ronnie.
Yeah, so I'm curious about your view of the future of NCAR, especially its relation with universities. In other words, a lot of research is being conducted, a lot of equipment is being purchased at NCAR, but there is a lot going on at universities as well. And I am really curious about your view of what the future is going to be for both type of institutions.
Thank you, Ronnie. And I forgot in my final slides to talk about that, actually. I was running out of time, so I wanted to hustle. But yeah, I think we have to re-envision, personally, and I've talked about this at NCAR, I think we have to re-envision our relationship with the university community. NCAR, as you know, was started because people couldn't, universities couldn't afford computer models to run, big models like Amy, do research like Amy and Jeremy are doing. And also, we operate an airborne platform, and universities couldn't afford to operate planes except you. But the university community, to your point, I think, has evolved. And, you can do simulations, very sophisticated simulations on a laptop, and people have Linux clusters. And then now there's the cloud, as I talked about. There's the cloud that's there. So I've thought about it, and we're thinking about it. How can we continue to sort of stay, nimble and keep up with the needs of the university community? One of the things that I've put out there, and don't ask me how to do it yet, but one of the things that I've put out there is talking about hubs, and the idea is that I think that historically we've been too focused on Boulder, on NCAR and going to Boulder. And so what we're thinking about, how can we sort of reach out more and be present in the university community? And so we're thinking about these concepts of hubs. And the staff gets nervous when I talk about that, because what they think I'm going to do is I'm going to sort of, send them all to work across the country. But no, what we're thinking about is like here in Miami, there's a particular focus here: marine science, tropical cyclones, and that's what you're focused on. And so, and obviously there's work that we do at NCAR, and people come to NCAR to work on that, but how can we come and have a presence, somewhat of a presence here, and be catalytic in the work that you're doing, and work with other universities that are around here? Again, it's a concept right now, but it's definitely in recognition, to your point, it's in recognition that the needs and capabilities in the university community have changed and is changing, and how at NCAR we can stay up with that and continue to support it. Because that's our mission. The mission of NCAR is not to do esoteric research in Boulder. It's really to enable science in the university community. Sorry for that long-winded answer, but you gave me a chance to say something that I wanted to say, but I forgot.
I had a future tense question as well. With all this dynamo that you created with the interactions across these different disciplines, do you see anything that really, like, again, future tense, fascinates you as a slight possibility, but might just blow the doors off of things? I love to hear that stuff.
Yeah. What I'm really curious about, and I think is really hard, and I don't know if it's going to blow the doors off of things, but I'm really curious about the interaction between physical science and human dimension. And so in other words, think about our models. Again, the model that Jeremy talked about. Think about a future forecast. Human dimension, society, how we interact with each other, our economy and all that is also dynamic and can be modeled. So I'm really interested in someday, and it's a really hard problem, right? But in someday coupling the physical prediction system with the human dimension system to see what happens.
Yeah, I had a question. I don't really think I need a microphone. We haven't discussed the big elephant in the room, namely climate and global warming. And you want to react to these events that occur and predict them better and focus in on their results of interaction. But it seems to me that the big elephant in the room is global warming. What is NCAR doing not to influence the government, the politicians, to make changes fundamentally about the chemistry that's going on? I don't hear any of that in your discussion.
Yeah, because I've been beaten into being speaking politically correctly.
Well, administration hopefully won't like that.
So yeah, and I think that that's partly true, is because that I think as climate scientists, some scientists, not all of us, over the years have been careful in how we speak. But this is all about climate change. Increasing fires that we're experiencing is about climate change. Increasing extremes is a response to climate change. And at NCAR, again, the models that Jeremy and Amy talked about are climate models. And we're investing in most of the money that we invest at NCAR is into developing these climate models to understand and study the climate. And as I get, again, I apologize for not being clear, but a lot of it is all about climate change. And in fact, remember I talked about 4 big societal issues: public health, infrastructure. But again, the last one we talked about, the 2 last ones, one was in extremes and one was on, in response to climate, is all about climate. And so at NCAR, we're investing in terms of research dollars into developing climate models that study and understand the climate. And I think in the context of this discussion about actionable science is exactly that. It's not just sort of being curious about how the system works, but in connecting with other stakeholders, decision makers, engineers, for example. That in the example that I gave with respect to a flood prediction in the future, we want to understand the needs of water resource managers and city planners, so that they're able to to build infrastructure and plan for the changing climate. And so, as you know, there's adaptation and mitigation. I think a lot of people are now, where we are is sort of focusing on an adaptation strategy. And we're very much a part of that. I'm going to go to, did that, am I still kind of being?
Well, it's like gilding the lily. Address these small issues when the big issue is the fact that the temperature of the Earth is changing, and we're not doing enough to reduce that. And it's an atmospheric problem.
So again, I would argue that a lot of what we're doing at NCAR is really focused on that, and really helping society through the science that we do to understand and to respond to deal with that. We're not political, so we're not going out there to go, we can't be political, but we're providing the information, one, for the public to respond, but also to use how it wishes.
The beauty of meteorology is that we work at the whole Earth. We observe the whole Earth. We work together, climate over the whole Earth. And these problems are great for the United States of doing all this work. But what about the rest? Are you making these models for other areas?
Absolutely, it's for the goal. We work internationally. We can chat afterwards. I don't. Yeah.
How do you personally deal with the problem of collaborative versus possessive? You're bringing people together in a collaborative environment, but yet you tend to be possessive of your research. In the private sector, I've dealt with that in many different ways, but you're not the private sector.
Yeah, it's a good question. My problem is I never think I'm the smartest guy in the room. So I think if you approach it from that way, then you want to kind of learn from other people. And I hear you. I mean, when, for example, we take our scientists to talk to the public, and especially when we take our scientists to talk to politicians to try to seek more funding for climate change, for example. One of the things we talk to our scientists about when you walk into a room, don't act like you're the smartest person in the room, and really communicate in a way that's from learning, from educating. And so I think when you're working in teams, I think, so you asked the question personally, and obviously I have my own biases, but I really fundamentally believe you get to a higher place from kind of working together.
Well, I think you, being the leader of the program, have to encourage collaborative
Yeah, absolutely.
work, where it's hard to do that.
Yeah, it is. It's very hard. In fact, Ronnie and I
Information a lot of times.
Ronnie and I spent a whole hour talking about, and I was explaining to Ronnie, how hopefully nobody from NCAR is listening to this, but talking to Ronnie about how, the way we're divided into, we do atmospheric science, right? We do atmospheric science. And believe it or not, we're divided into something like 6 laboratories. And those laboratories are stovepipes as it exists right now. And one of the things that I'm doing at NCAR is really, and me and my leadership team, we're really trying to break down those stovepipes. And so those are stovepipes not between atmospheric sciences and sociology. That's stovepipe between climate, meteorology, air quality, and air quality. So absolutely.
All right, everyone, this will be our last question of the night.
Does NCAR have anything in its arsenal that can bust a cyclone, a typhoon, a hurricane in the atmosphere, a shield, as it were? Is there anything that we're doing to actually control the atmosphere before it devastates us?
No, we don't have anything like that right now. However, there is, however, there is research, and it's termed geoengineering, and it is research. It's mostly focused on climate, and how is there a way that we can artificially influence climate change, for example. It's controversial, because somebody said, for example, one saw a talk, and so basically there are different techniques. So for example, there was one study way back where you flew a bunch of 747 filled with salt, and you released them in the upper atmosphere, then they would cool the planet, right? But subsequent research has shown that that's risky, because the temperature doesn't change uniformly, right? Because it's a dynamic system. And so I saw this talk, and somebody said, well, how do you decide what thermostat? Are we going to go to the UN, that great deliberative body of consensus, to decide what temperature we choose? And the temperature, obviously, 78 degrees. But it's not going to be 78 degrees all over the globe. So at NCAR, we've decided, actually, and this is controversial in the scientific community, at NCAR, we've decided to get involved in that research because we think ignorance is the worst thing. And politicians are very interested in this solution as an easy solution, if you will, rather than doing the hard stuff like reducing emissions and whatnot. And so, but in NCAR, we've decided to get involved in this research to, again, provide more information, better information, to avoid a decision that could actually, be consequential, globally.